Okay, you guys should have the note sheet for this hopefully already printed out. We're going to be doing section 11.3, solving differential equations. Diffie for short. A lot of my college professors would say it like that, but I'll probably just say differential equations. But a differential equation is any equation that has a derivative in it. So here's a crazy example. But we've been dealing with derivatives since first semester, and we've been undoing derivatives quite a bit this semester with integrals. So this isn't a brand new idea, and I've been actually having you guys already do it on homework assignments this chapter. So this is sort of the formal lesson on it. But here's some examples of derivatives we've tried to undo and talk about with motion. Now there's two different notations that we often use with derivatives, and this one probably our favorite a lot of times because it's easy and quick. This was Newton's notation, and convenient, quick, doesn't take ton of work. And but the other one was using multiple variables, and that one was Leibniz notation, and that one I think is going to be a lot easier to work with actually with solving differential equations because we have to separate the variables. So we're going to be going with this kind of notation usually when we're solving differential equations. Now, the equations that we've been undoing the derivatives for this chapter or this semester have usually been kind of easier because they only involved one variable, but we're going to start to see derivatives with y's in them, and that makes things a little more interesting. So here are the key steps for solving a differential equation, and all the equations usually I'm going to give you on homework are separable, meaning you can separate the variables, and also on the AP test. So you don't have to worry about some of the examples I've been showing you in the last few days. Generally, in the AP test, on a free response question, this is worth like 5 or 6 points out of 9. So that's a lot of points that you really want to make sure you get. As far as free response questions go, these are kind of a little more easy to get these points. So just separating the variables is worth 1 point. The problem is if you don't separate the variables, if you don't do this, you're going to get 0 out of 6 points. Whatever you're doing isn't going to make any sense, so you don't get any points. So you want to make sure you separate the variables. Then we're going to integrate both sides. That's 1 or 2 points. Maybe 1 point for one side, 1 point for the other. Maybe just 1 point total. It kind of depends. Don't forget the plus C. Just writing plus C is worth another point. Just writing plus C. That's the constant of integration that we usually use the initial condition to find the value of. That's another point. If you don't put the plus C, you lose all the rest of the points. Then we got to solve for Y, which is usually some algebra. And this might be 1 point combined with parts 4 and 5. This is usually kind of the most labor intensive part, but also the least calculus type of work, more algebra, trying to get Y by itself. Now, also the other thing that I've been mentioning is that you need to make sure you include the domain in your answers for the solutions from differential equations. This is not usually a requirement for other problems, but you need it. It's kind of like, this is my answer, and the domain is saying this is where you're allowed to use it. Okay, so we're not allowed to use it at any places where the equations domain doesn't exist like normal, but you also need to, so you got to break it up at any discontinuity like normal, but you also, this is the key part, you have to break it up at any point where the derivative doesn't exist. That's usually not an issue for domains of just equations in general. And even beyond that, so like that means a corner, a cusp, a vertical tangent, anything where the derivative is undefined, you got to break it up there. And then you got to pick a single open interval that contains the initial condition. So this is a little different. We only are going to pick one chunk. Domains usually can have several chunks, but we're only going to pick one piece of it and it's got to be open, which means open dots, parentheses, and interval notation cannot include the endpoints for sure, even if they would normally be okay. And you only can pick the one chunk that contains the initial condition, because that's where this problem originated from. So we have to kind of recognize that. So here's an example. Let's go ahead and do the slope. Let's do the slope field. And right now, what you should do is probably pause the video so that you can try it yourself. So my videos don't get too long, I'm going to go ahead and keep going, but pause it, let yourself do the slope field. Now, we could also get rid of this outer boundary just because that's a lot of dots, and that'll cut down the amount of dots by like half. Let's just get rid of that. But let's try it just to practice our slope fields, which we've already been doing quite a bit of. But pause the video right now, do your slope field, unpause it, and then you can watch me do my slope field and compare yours to it. But I'm going to go ahead and do the slope field now. So I'm looking usually for 0 slopes, and in this case, I'd be where x equals 0, which is the y-axis. So this is the y-axis. So we're going to get 0 slopes along the y-axis. So I'm usually looking for patterns. So maybe, I don't know. Might also look for undefined slopes, which might be undefined because they're vertical, but it could be undefined for other reasons. This one's going to be division by 0. So that's when y equals 0, which is the x-axis. And you technically aren't supposed to draw these, but I'm going to draw them just because they kind of help us understand the behavior, what's going on. Because the curve actually does have vertical tangent lines there. And I look at some other values like, when x and y are the same value, it's going to be 1. So when they're both positive 1, it's going to be negative 1. When they're both positive 2 and 2, it's going to be negative 1, 2, 3 and 3. Negative 1 and negative 1, negative 2, negative 3 are going to give you negative 1 slopes all along those. Now, if we pick negative 1, positive 1, it's actually going to turn out to be positive. So if they're the same number but different signs, you're going to get positive 1. So we crank out a bunch of those. In between, we're going to start to get some other, different values. 2, 1 is going to be negative. Let's see. The x value is 2. So that's going to be negative 2 slope. So I'm looking at these dots. I'm like, all right, negative 2. And over here, when x is negative 2 and y is negative 1, you're going to get negative 2. When x is negative 2 and y is positive 1, actually you get positive 2, positive 2, positive 2. And when x is 1 and y is 2, you're going to get 1/2, negative 1/2, down 1 over 2. I'm looking at these dots to try and line them up right. And this one's also going to be that. And this is going to be positive 1/2. This is going to be positive 1/2. So there's our slope field. Now, if you're to look at this, you can, now hopefully you got your slope field. If you're going to look at this, you should be able to see maybe some kind of familiar shapes or family of shapes, like a bunch of them that are either shifted up or down or different sizes. And I kind of think this looks like a family of circles. Now, they gave us an initial condition, which we've ignored. So we could try and sketch that in. That would be negative 1, 2. So I'd identify that dot, maybe make a big deal. Oh, hold on. No, I messed up. X equals 2, y equals negative 1. So it's down here. So this is 2, negative 1. And I usually make a big deal about it. And then we're going to follow this. Now let's do it lightly first. And you should, kind of go through this and go from one slope to the next. You shouldn't be crossing slopes. This is just kind of a rough process, but I don't know, we get something kind of like that. It kind of looks like a circle. Now, I did it lightly because technically that whole thing is not the particular solution, because the whole domain issue I was talking about before, that applies to graphs also, because these are pictures of the solution. So right here and here, the derivative is undefined. So we got to break it up there, any points where the derivative is undefined. And then is it the top half or is it the bottom half? And so that's where we use our initial condition. We say, well, our initial condition was on the bottom half. So this is the part of it that is actually our particular solution. and we're not going to include the top half unless we got an initial condition to start up there. So this is that domain issue, and it's only going to be that chunk. Also makes sense from just the idea of a function, like functions have to pass the vertical line test. If we kept the top and the bottom half, it would, you'd have to actually write two different functions to get the top and the bottom halves anyways. The whole plus or minus thing would probably decide to do one or the other. So that's the visual of the solution of a differential equation. So now let's go to looking at finding the solution with, not visually, kind of algebraically. So we'll break it down as the main steps that I described up above. So I'm going to go ahead and just rewrite it. dy dx equals negative x over y, and our initial condition is 2 comma negative 1. That's your x and your y that we'll use later to find the c. And so let's separate the variables. Usually you do that by multiplying or dividing both sides. We definitely want the dx to be over here. So we're going to actually break up the dy dx. So dy is over here, dx is over here. We want all the x's to be with dx and the y's to be with dy. That's what separating the variables means. So I'm going to leave the negative on the right-hand side with the x, and then the y would get multiplied to the other side to get out of the denominator. So that's worth a point. You don't want your dy or your dx to ever be in the denominator, so make sure you don't do that. So usually the dy's end up on the left side, dx ends up on the right side. Now, leaving the negative on the right, that's just my personal preference of, like, when we're done, we're going to try and get y by itself on the left-hand side. So the less stuff we move to the left side, the less stuff we have to move back. So then we're going to integrate both sides. And so the antiderivative of y, the first, is power rule, y squared over 2. And this is going to be negative x squared over 2. And then we got to do the plus c. Don't forget the plus c. If you do, you lose all the rest of the points. So now, it doesn't really matter, like, oh, should we put plus c on the left side and the right side? It doesn't matter. So I usually just do it on the right side. If we can combine them together, again, I want to keep as much stuff on the right side as possible. So let's just put the plus c over here. Now, let's find the plus c right now, because dragging it through the rest of our work to get y by itself is a pain. And it's going to be easier if there's like an actual value there, I think. So let's find that right now. You can find it at the end, but I think it's kind of a hassle. So we're going to plug in negative 1 in for the y and plug in 2 for the x. I'm always careful about plugging things in parentheses. So we get 1/2 equals negative 4 over 2 is negative 2 plus c. And so c equals, we're going to add 2 to both sides. C equals 2.5, but let's rewrite that as 5/2. That's going to just be easier to work with. I don't think we want mixed fractions and stuff in our work. So then we're going to rewrite it. Y squared over 2 equals negative x squared over 2 plus 5/2. And now for the tedious getting y by itself. So, I'm going to multiply both sides by 2. That's going to give you y squared equals negative x squared plus 5. I'm going to take the square root of both sides, plus or minus. Now, we should decide right now if it's plus or minus. It's a particular solution, so it should be one or the other. And so go back to your initial condition and say, okay, well, if I plug x equals 2 in, I should get negative 1 out. So if you plug 2 in here, square root is 4, negative 4 plus 5 is 1, square root of 1 is 1, but we want it to be negative 1. So we got to go with the negative here. So our answer is negative y equals negative square root of negative x squared plus 5. Now that's just the equation. And so we need to now figure out the domain. So that's always this extra step people just tend to forget. And you'll lose that last point if you do. So domain, we're looking for different issues. We're looking for just this right here. Like, okay, well, we know that domains of even root functions, the inside has to be greater than or equal to 0. Now, this is a, Usually what I do is I just say, oh, well, let's just look at this is easier than normal because we're going to just pick one section of it. So we don't have to go through all the inequality checks and stuff. So we could just say, all right, well, x squared equals 5, square root of both sides, plus or minus. So x, normally x can equal plus or minus 5, but I'm gonna make a number line and say, okay, well, those have to be open dots. We said the domain is a single open interval. So anything that's going to break up the domain needs to be an open dot, no matter what, even if it was okay up here. The other issue that we have to think about for domain is the original derivative ever undefined? And this is negative x over y, and y can't equal 0 because then our derivative is undefined. We don't put 0 on here because that's a y value, and we're trying to figure out domain, which is x's, but that doesn't mean we ignore that, because y equals 0 for a certain x value. In fact, we just found it. When does you could set your new solution equal to 0 to be like, okay, it can't be 0, so what's the x that it can't be? Well, that was that plus or minus root 5 that we just found. So a lot of times the issue with the domain of the answer might be tied to issues with the derivative. That's not always the case. We're going to see some that's not the case. So this is our number line. Now here's the easy part. Instead of having to do line checks and figure out where this is true or false, we just say, well, where's the initial condition? And you might estimate these. This is like, I don't know, it's like 2.2 or something negative. This is like 2.2. So 2 negative 1 is like right around here. Now I'm just writing that on here. That's not going to affect that's not going to be part of my domain, like as far as like an endpoint. And so we say, oh, this whole chunk right here, that's the domain. So we write our answer up here. This is our answer, but we say that it works for negative root 5 to positive root 5. And that has to be included in your answer to get full credit. So the domain is going to be a little bit of a challenge, I think, for some people. I mean, one, people are just going to forget to do it. And then two, they're going to just have some problems trying to figure it out too. But anyways, so let's go back to the worksheet. Now I'm doing this at, I guess, just the right time of day, that there's like sun shining through the window, which is nice because it's not raining anymore, but then it adds glare. It messes up the lighting of this. So I don't know. I'm having to do something a little weird. I mean, I guess I could move this. There we go. That might be a little better. So why don't you guys go ahead and try and start to do this problem? Maybe pause the video and just give yourself a chance to try this out. See if you can separate the variables, and then you got to integrate both sides. Now, when you unpause it, if you're having trouble, then unpause it, see me do the next step, and then pause it again and see if you can keep making progress, and then unpause it. Okay. If you just watch me do it, you're not going to get that great at it. If you can't do it on your own, then just watching me do it isn't going to help you that much. You got to try it. So pause the video right now. I'm going to go and start doing it, and you can unpause it as you need help, or after you're done, unpause it, see if you did it all right, and make some corrections. So I'm going to go ahead and start. So I'm separating the variables. Now this all has, oops, I messed that up. We want the y to go to the left-hand side. So it's going to be dy over e to the y. It's going to end up in the bottom. And over here, this is going to be 1 over 1 plus x squared dx. Okay. Now, we're going to integrate both sides. Now, over here, don't say natural log. That's not going to be natural log. You want to think of e to the negative y. And what's the antiderivative of e? It's itself. Now, there is a little chain rule issue there that you could do u substitution on, but I feel comfortable enough to be like, well, I need an extra negative. It's not power rule. Okay, it's just e to the negative y. When you take the derivative of e to the negative y, it's going to be e to the negative y times the derivative of what's inside, so we need that extra negative to get canceled out. Now, the right side, you might be like, oh my goodness, this is hard. You could try u substitution. And du equals 2x dx. That's no good because it has an x and we just want dx. This is one of those special rules that you got to know. That's inverse tangent. So inverse tangent of x. We just got to memorize it. So it's inverse tangent of x plus c. Now, like I said over here, we could have done u substitution. U equals negative y, du equals negative 1 dy. We don't want the negative. So then we rewrite it negative e to the u du, and its antiderivative is e to the u, and then you plug it back in and you get that. That's a lot of extra work for just that. Now, if that's what you need to do, then do it. Okay, let's find the c now. So we are given an initial condition, x equals 0, y equals 0. Let's plug those in. E to 0 is 1. It's not 0. Inverse tangent of 0 is asking you, what would you take tangent of to get 0? And I don't necessarily memorize all those. So I'm thinking in my head, what do I take sine and cosine of? That in a fraction would give me 0. So really it's just when is sine equal to 0 and its principal angle. So it's going to be 0. So sine is 0. And so that's going to be 0. So c equals negative 1. So we got that figured out. So we're going to plug it. I'm going to rewrite it, plug it back in. Negative e to the negative y equals inverse tangent x minus 1. Don't lose that negative over there. This lighting is killing me right now. Okay. It's just getting worse. Let's see. But then it's kind of dark. Okay, now for the fun work of trying to get y by itself, which is not super fun. But I'd get rid of the negative. I multiply everything by negative first. And then how to get rid of e? You say, well, I take the natural log of both sides. Right? So we take the natural log of both sides. Now, you can't break this up unless you have some natural log rules, but we can't break that up. You got to take it the whole thing. Now, over here, the natural log and e undo each other. You have a negative still, negative y. This is all one big natural log. And then we get divide by negative 1. So we get y equals negative natural log of negative inverse tangent x plus 1. It's kind of a crazy answer. Now we still got to find the domain. So the domain can be tricky. There's some different issues we have to work with. Is this one? We can't take natural log of 0 or negatives. So whenever this is 0 or negative, we got it. So I'm going to write that up here. So we're going to start working on domain up here. It might be good to write that in your work or on tests or whatever, just to kind of let me know that's what you're thinking. So the inside of a natural log has to be positive, right? Now I'm going to just say, well, when does it equal 0? Because that's the point. And it's a little easier on these to do domain because we only are going to pick one single outcome in the end. So we can kind of ignore the inequalities because we can find it with the initial condition when we're done. So let's see, inverse tangent x equals 1. Subtract 1, divide by negative. So then how do you get rid of inverse tangent? You say, well, then you take tangent of both sides, right? Tangent of both sides. And those cancel. And then you say, well, what's tangent of 1? Well, that's sine of 1 over cosine of 1. We don't know what that value is. So I guess we're just going to stick with this. x cannot be tangent 1. So that's going to go on our number line. Another issue is tangent itself. But inverse tangent, its domain's all real. So if you guys, I don't know if you guys remember, this is the graph of inverse tangent. So its domain's all real. So that's good. If it was regular tangent, tangent has some domain issues. Inverse tangents all real. So that's good. That's good. And then we also need to make sure we look at the original derivative. Is the original derivative ever undefined for any reason? And in this case, sometimes it's division by 0, sometimes it's other things. So right here, that 1 plus x squared can't equal 0. So if we solve that, and I'm going to want to see this in your work, just make sure you thought of it. But if we take the square root of both sides here, plus or minus, we get imaginary, we get I. So that's fine. We don't need to worry about that. So then usually what we do is I then do a number line, and I put any of these values on here that cause problems. And the only one we got was tangent of 1. So I'm going to put an open dot at tangent of 1. And then our domain's going to be one side or the other. But the easy thing is we need to figure out where the initial condition lies relative to that. Now I just drew a graph up here. This is tangent of x, right? So tangent of 1 is definitely over here. Tangent 1 is definitely positive. So 0, x equals 0 is definitely going to be on the right, right? So then that has to be our domain. So our domain, we're going to write our final answer. We're going to say for negative infinity to 0, parentheses. That's your full answer. All right. So this other problem is just sort of a interesting kind of challenging question. You guys know when I say challenge, that means it's fun, right? Find family of curves for which the slope of the tangent is twice the slope of the line connecting the point to the origin. And what are they even talking about? Let's see if we can just draw some kind of rough picture. So we have some curve, just generic, and you have a point, and it says for which the slope of the tangent. Okay, so tangent, that's like a tangent line to the curve. So you have a tangent line to the curve, twice the slope of the line connecting. Okay, so we have a tangent line, and then we have a slope from the line connecting the point to the origin. So that's a different line. And we're trying to figure out, is there a certain family of curves where this is like always true? So now at any point on the curve, it has an xy coordinate, right? So the slope of this line, if we're going, what's the slope from 0, 0 to any xy? The slope of the line is going to be change in y over change in x. So we for sure know that the slope of the line is always going to be y over x. And the derivative, the slope of this line, well, we're going to call that dy dx, whatever function it is. And so let's see if we can write this statement up here in terms of like an equation that involves derivatives, a differential equation. So we're saying that the slope of the tangent is twice the slope of the line connecting the point to the origin. I'm just trying to, sorry, you guys can't see that. Slope of the tangent equals 2 times the slope. So the slope of the tangent is dy dx, and the 2 times the slope of the line between the origin. So the slope of the line between the point and the origin was y over x. So that's going to be 2y over x. So what we did was we just created the we just created a differential equation for what they're describing. So now we can go ahead and solve it. We could separate the variables. We want to bring the y over to the left, dx over to the right, leave the 2 on the right. I just think that's what I would do. So that's called separating the variables. Then we're going to integrate both sides. And we're going to get natural log of the absolute value of y equals 2 times natural log of the absolute value of x plus c. We can't find the c value this time because it's a general solution. They didn't give us a initial condition. So we're just going to find a family. That's why he said family of curves instead of one specific curve. So we need to exponentiate both sides. Now, rules of exponents say that you could break up this like that. You can't distribute the exponent, the e to the whatever. You can't do that. But what you could do, over here, you're going to get absolute value of y. This will cancel. And here, you have to bring the 2 in before you can cancel the e and the natural log. They can't be anything in between them. And the e to the c, I'm just going to call c. I don't know if you guys have caught on to that yet. C is a constant. E to the c is a constant. So I'm just going to write c for that whole thing. I'm just going to say c. So I'm going to write c absolute value of x squared, because I brought that 2 in log rules. Now, the fact that it's squared, the absolute values aren't necessary anymore because that's going to force it to be positive no matter what. And then to get rid of these absolute values, I'm going to do plus or minus cx squared. And, that's our general solution. I'm not going to do domain for it because it kind of depends on the initial condition. So, it's the family is parabolas, right? Family of curves where this is always true are parabolas. So, anyways, just kind of interesting problem. So, I am thinking. Let's see, we could maybe do the first couple problems on tonight's assignment together. So hopefully you guys already have that printed out. If you don't, pause the video and print it out. And so it's a multiple choice worksheet, or part of it is. So we just try a couple problems right here just to make sure you have the hang of it before we go on. So if you have it, I don't know, go ahead, see if you can start trying it. But just because it's multiple choice doesn't mean it's less work. I mean, it's going to be possibly more work because your answer might not be there. But here's our differential equation. Here's our initial condition. It involves time. So whatever, time instead of x. So it's like 0, 1. What is the value of t for which y equals 1/2? So I guess we have to solve the differential equation. And then we have to set our new answer equal to 1/2 and solve for t. So this has a couple layers in it. So let's separate the variables. If you haven't done that yourself, pause the video, try it yourself. So I'm going to bring the y over here, bring the t's over here. That's separating the variables. I'm going to integrate both sides. Antiderivative -2 is just -2t plus c. Don't forget the plus c. Now we have initial condition. I'd find that right now. So I plug 1 in for y, 0 in for t. That's going to be 0. Natural log of 1 is 0. You guys should all know that. So c equals 0. So we're going to rewrite it. Natural log of the absolute value of y equals -2t. That's it. So now let's solve for y. You know what? I think I just realized a shortcut. We could, if we want to know when t is equal to what t is when y equals 1/2, let's just plug that in right now. So this is my shortcut. I'll do it the other way in a second, but we can just plug that in. And then t equals -1/2 natural log of +1/2. Now, if you look at the list, I don't see it there. Oh, there's a negative. I should have a negative. I don't see it there. So this is where multiple choice can get tricky. you got to realize that maybe you can manipulate this answer to get one of those. So one of the things we could do is we could bring this whole thing inside, and that would give you a square root. And you do see one answer with square root, which I'd be scared to pick. So maybe don't bring that whole thing, but if you just bring the negative in, then you get 1/2 natural log of 1/2 to the -1, which is the same thing as 1/2 natural log of 2, which is answer C. So, I don't know, tricky. Anyways, if we were to keep going, sort of the longer route, get y by itself, we would exponentiate both sides. And that would get rid of that. And then we get rid of the absolute value by doing plus or minus. We would pick one of those answers for sure based off the initial condition. If you plug 0 in, you should get +1 out. So 0, either 0 is 1, you want the positive. So that's our solution to the differential equation. Then we can set it equal to 1/2 and then solve for t. What's going to happen though is we're going to end up redoing the work we just undid to get t by itself. So we're going to take the natural log of both sides. And then we're going to divide, that'll get rid of that. And then we're going to divide by 2. So you get -1/2, natural log of 1/2. And again, that answer is not on the list. So you got to do the stuff we did up there to get that. And then let's see. Sun is not working with me again. I guess I'll think of this in the future, but I don't want to redo this. At each point in a certain curve, the slope of the curve is. So the slope, well, that's like y prime, right? Or dy dx might be a little more useful version. If the curve contains this point, then the equation of the curve is what? Well, this is initial condition. So this is just like questions we've been doing, but worded a little less straightforward. So what we're doing is we're solving a differential equation, and we have an initial condition 0, 8. So there it is, kind of written more in simple terms. So we got to separate the variables. Dy over y equals, I'm going to leave the 3 on the right side of the dx squared, which works out really nice this time. And we're going to integrate both sides. This is natural log of the absolute value y. You need the absolute values. This is going to be x cubed plus c. Let's find the plus c now. Plug 8 in for y, 0 in for x. So c equals natural log of 8. Rewrite it. Natural log of the absolute value of y equals x cubed plus natural log of 8, which seems like a really annoying value, but it's going to work out nice. Exponentiate both sides. Remember, rules of exponents allow you to break this up, which I think you'll want to do, especially since this is multiple choice, by multiplication, and that's going to just give you 8. Now, to get rid of the absolute values around the y, we're going to do plus or minus, and there's just going to be an 8 in front. E to the x cubed. It should be plus or minus. If I plug 0 in, I should get +8, which means we're going with a positive here. So our final answer is 8e to the x cubed. Now, we see that answer there, answer A. That one wasn't weird. So that's it. Try the rest of this homework, check your answers, and vote in the Google form that I'm going to send out so that I'll do the ones that you want.